Okay, so let me, just because this guy is a little bit small, let me rewrite it a little bit bigger. So if we have an estimator theta hat, and we subtract off its true value, theta, and divide by its standard error, sigma of theta hat, right? So that's the square root of the variance of theta hat. That often has a normal distribution, normal 0, 1 distribution for large sample sizes. If there's some sort of IID-ness built into the problem somewhere, like our IID errors. And then often if we replace that sigma with its estimated version for small sample sizes, for large sample sizes that also tends to be normally distributed, and often for smaller sample sizes it tends to be t-distributed if we have assumed normality at some point, but the t-distribution has nice fat tails, so assuming a t-distribution often isn't the worst thing to do anyway. Okay, so it is normally it's often normally distributed and has a finite student's t-distribution as the estimated variance is replaced by the sample variance, and we can use that to test or create to test things like theta equal to theta naught versus some of these alternatives, like what I mean is HA theta greater than theta naught, or HA theta less than theta naught, or HA theta not equal to theta naught. Okay, let me get rid of all that stuff just because it's clouding things up a little bit. And then we can also use it to create a confidence interval for theta, and our confidence intervals usually look like theta hat plus or minus an appropriate quantile times the estimated standard error, where the appropriate quantile is, you have this distribution, and we want it so that alpha over 2 is in the upper tail, so 1 minus alpha over 2 is in the lower tail. And that quantile is Q 1 minus alpha over 2, and usually this is either a t or a normal distribution. And then, so when you took your inference class with IID sampling assumptions and Gaussian errors, our inferences are going to just follow what you saw in your inference class. In fact, all of the intervals we covered in the inference class for continuous group data, for example, the two-group t-test, they can all be viewed as sort of special cases of these regression type estimates. And we're not going to cover asymptotics for regression analysis because you have to make some assumptions about how the X process is going to infinity as well. If you have bivariate Gaussianity, then it's certainly no problem. Or if you have an instance like ANOVA or something like that, where the X's are specified into groups with some assumptions about how the X's go to infinity within the groups, then you're fine. But that's maybe a bit much. Suffice it to say, then under very relatively broad settings, the asymptotic normality will also help you, and there you don't need, actually need normality of the errors. You just need the sampling assumption that they're IID, and some assumptions about how X is going to infinity. Those two things will give you all the asymptotics you need. And when we switch over to generalized linear models, that's what we'll take advantage of. But we're not going to cover that because it's a bit advanced. Okay, so let's derive the variance of the slope coefficient just to show you how these calculations are done. It's a lot easier if you actually know the linear algebra, but in this case we can do it pretty simply on our own. So what we want is the variance of beta 1 hat. And then in this line right here, all I've done is replaced beta 1 hat with its estimator. Then remember that because summation yi minus y bar equals 0 and summation xi minus x bar equals 0, that we could write summation xi minus x bar yi minus y bar, we could write that either as summation xi minus x bar times yi, or as summation yi minus y bar times xi. Either of those works. You can work out the arithmetic. So we can get rid of one of the bars, x bar or y bar, and we get rid of those, and we come down to the next line. Oh, and then if you pull this whole guy, which remember we're conditioning on all the x's, if we pull it out of the variance calculation, it gets squared. Okay, so that we're at that line right now. Now the yi's are all independent. They're not identically distributed because they have different means, but they're independent, so we can move the variance across the sum. And when we do, if we pull the xi minus x bar part out, it gets squared, and variance of yi is sigma squared, so we get that. Sigma squared doesn't depend on I, and then what we'll have, I'll just rewrite this right here, we have sigma squared summation xi minus x bar quantity squared over summation xi minus x bar squared quantity squared, and that cancels with one of those, and we wind up with this expression right there. Okay, so again, that's just for people who enjoy those kinds of details. Otherwise, what you could say is, okay, well, here's the variance for beta 1 hat, and then you could do the same sort of exercise and derive the variance for beta naught hat. And of course, we don't actually know sigma, so we replace it by its estimate. And then under IID Gaussian errors, this expression, the beta j hat minus beta j over its estimated standard error, follows a t distribution in n minus 2 degrees of freedom. So if you're used to the single group t-test, then you'll have noticed we lost an extra degree of freedom because we have to estimate one extra thing than we normally do. And then for a large n, it follows a normal distribution, and you can use this to create confidence intervals and perform hypothesis tests that you already know how to do at this point. So let's go through the diamond data set one more time. So again, here's loading the data and getting the correct library. I'm just defining the x and y's and n's just to avoid having to type the $sign. We could type LM and get beta, but of course we can always just define beta the old-fashioned way. Since we know how to do it on our own, we could get beta 0 as the mean, as this definition, mean y minus beta 1 mean x. We could define our residuals this way. We could get our estimated residual variance as the average squared residuals, but we're going to get our nice unbiased estimate, we'll divide by n minus 2 instead of n. So instead of the average residual, we'll divide by n minus 2. I just for notation's sake, the sum of the x's minus their means squared, I'm going to just call SSX for sum of the squared x's. Okay? And then my standard error for beta naught is this guy. If I plug into my formula, my standard error for beta is sigma over square root SSX. And then I'm saying that my t distribution for beta naught for a hypothesis test of h naught beta 0 equals 0. Why would I write beta? H naught beta 0 equal to 0 versus HA beta 0 either greater than, less than, or not equal to 0. Then that would be this t statistic right there, and then there's our t statistic for beta 1. And then if we wanted a p-value, we want the probability. Let me just draw it. Let's say for beta 0, if we wanted a p-value, we'd want, if our statistic was positive, we'd want to take that area from the t distribution and then multiply it by 2. If our statistic were negative, we'd want to take that area and multiply it by 2. So kind of the easy way to do that is to just take the absolute value of the statistic and say lower tail equals false. Or if you didn't even want to write absolute lower tail equals false, you could just force to get the negative one by putting a negative sign out front. Just make sure that degrees of freedom are n minus 2. You want to multiply your p-values by 2. If you get a number bigger than 1, then you've taken the wrong area, right? You've gotten the, instead of getting the small part of the tail, you got the big part of the distribution. We could do the same thing for beta 1 right there. And so, you know, here I just create a little table of all these values, and then I add the names for them as the estimate, standard error, t-value, the probability, and so on. Okay, there we go. And here's the result of those calculations. Now, of course, we don't do this when we actually create these kinds of tables. We instead just grab them from LM, right? So summary. So here I'm just fitting y as outcome, x as the predictor. Summary of fit will print out lots of stuff, but it doesn't fit on my page. So I'm just grabbing the relevant output from summary fit. $ coefficients grabs the table, the t table. So here's the intersect column, here's the x column, and you can see, you know, of course, we get the same exact numbers, you know, so our formulas are right, and apparently we implemented them correctly, right? So they all agree. So that's how, anyway, that's how R gets that stuff, and so now you could get it too. So I think at this point you should be able to program, you know, the vast majority of what LM does, you should just be able to program from scratch if you wanted to. And then getting a confidence interval. You could, let's see, as a confidence interval, let's see, so if you want to grab the coefficients, you can do summary fit and then coefficients. That'll grab the table, and then the relevant elements of the table are the 1, 1 for the intercept, and then 1, 2 for the standard deviation of the intercept. I need to grab the correct t quantile, and then I want to add and subtract it, so I just multiply by c, -1, +1, and that gives me a confidence interval, and that gives me a confidence interval for beta 1. And so just to interpret that confidence interval, we're 95% confident that 0.1 carat increase in diamond size results in a 355 to 388 increase in Singapore dollars. Of course, once again, just like in the previous lecture, probably a 1 carat increase as this is expressed is probably too large, so we want to divide it by 10.